Hello friends, I am Miss Marks and you're watching Math for Juniors. Snail, where are you?
Hello friends!
What is this new avatar all about?
Cultural night, Miss Marks. I am participating in the cultural night of our school. This is my character.
Oh wow!
Please come to see me. I'm also performing Garba.
Wow, Snail! Be it religion, culture, dance, dress, India is so colorful.
Yeah, India is truly an example of unity in diversity.
Do you know India has unity in diversity in numbers also? Numbers can be written in various languages. Look at this chart. See, in this, numbers are written in different languages.
Amazing!
Numbers have always been amazing, Snail. You know, we can even play games with numbers, and such games have always fascinated a lot of people around. And not just that, it's the expanded form of numbers which helps in forming games.
Miss Marks, it sounds fun. I want to learn more about it.
That's great, Snail, because this is what we are gonna learn in our today's session on games with numbers. So, into the virtual world. Let's begin the module with this illustration. Rohan wants to be a cashier, so he has started using different piggy banks for different denominations. He divides the notes into denominations of thousands, hundreds, tens, and the coins into ones, twos, and fives, and places them in different piggy banks. Now, when he needs to take out some money, he can easily pick various denominations from the different piggy banks. Now suppose he needs 55 rupees. From which piggy bank should he pick money to build up 55 rupees? For this, he needs to have an understanding of how to break up or expand the number 55. So let's find out all about this as we learn how to write numbers in their generalized form and play number games with 2 and 3-digit numbers. Let's see how numbers can be expressed in expanded form. There will be different ways to break up a number. For example, the amount of 55 rupees. Here is one way. Rohan takes out 55 rupees out of his piggy bank as 5 10 rupee notes and 1 5 rupee coin. That means the number 55 can be written as 50 plus 5 or 5 into 10 plus 5. So, in general, a 2-digit number xy can be written as 10x plus y. And the number obtained on reversing the digits, that is yx equals 10y plus x. Now, what about numbers with 3 digits? Let's find out. Extending the same logic to a 3-digit number like 452. 452 can be written in expanded form as 400 plus 50 plus 2, which further can be written as 4 into 100 plus 5 into 10 plus 2. Let's generalize it. A 3-digit number xyz is equal to 100 into x plus 10 into y plus 1 into z, which is 100x plus 10y plus z. Now, if the position of the digits are changed, say yzx or zxy, then yzx is equal to 100 into y plus 10 into z plus 1 into x, and zxy is equal to 100 into z plus 10 into x plus 1 into y. So now you know how 2 and 3-digit numbers can be written in their general forms. Snail, I hope you understood it all, huh?
Yes, Miss Marks.
Okay, so tell me, what is the expanded form of the number 907?
It is 9 into 100 plus 0 into 10 plus 7.
Correct.
Math suddenly turns out to be a lot more interesting.
For any learning, the method has to be interesting. A playful method is like a cherry on top of the cake.
Cake?
Oh, stop dreaming, Snail. It's time for some interesting games formed with the help of numbers.
Wow, games! Then let's quickly enter the virtual world, Miss Marks.
Did you know that you can use general forms of numbers to play number games? Here is one such situation wherein no matter which number the other person thinks of, just by performing a particular set of calculations, you can guess the answer. It will always be 13. Like a magic spell. Don't believe it? Let's see how. Let's play this game. Okay, think of a number. Let's say 42. Now double the number. You get 84. Now add 15 to the answer. The result is 99. Now multiply this with 3. We get 297. Now add 33. We get 330. Now divide by 6. The result is 55. Now the last step. Subtract the original number from this result. Well, the answer is 13. This trick can be repeated with any number which is not more than 8 digits, and the final answer will always be 13.
I will show these amazing magic tricks to all my friends.
Would you like to know some more tricks?
Sure, Miss Marks. Tell me quickly.
Relax, Snail. I'll now tell you a trick in which, by taking any 3-digit number with all the digits distinct, you will always get 1089 on performing certain calculations.
Really?
Yes, you can try it out. So first, think of any 3-digit number having all the digits distinct.
Okay.
Now arrange the digits in descending order. Let's assume this number as A. Now reverse it. That is, now write your digits in ascending order. Let's assume this number as B. Now subtract B from A. Let's assume the answer as C.
Okay.
Now arrange C in reverse order. Let's assume this number as D. Add C to D. See what you get?
Oh God!
I told you the answer in the beginning,
It is indeed 1089.
Well, let's enter the virtual world to discover more such interesting mathematical games, Let's look at a few interesting tricks with numbers. The first one, adding a 2-digit number xy and its reverse yx will yield the number 11 times x plus y whole, which will always be divisible by 11. The second property, difference of a 2-digit number and the number obtained by reversing its digits is 9 times x minus y whole, which will always be divisible by 9. Both the above properties hold true for every 2-digit number. Now it's time for third property. For any 3-digit number, the sum of the numbers obtained by using the digits yields 111 times x plus y plus z whole, which is always divisible by 37, as 111 is 37 times 3. The above property is valid for every 3-digit number.
The 8th game was quite interesting, Miss Marks. Numbers are amazing.
More amazing fact is that there are different symbols for numbers in different number systems. Mayan number system is one such example.
Mayan numbers?
It is do you know time, huh? Do you know Mayan number system was a base 20 numeral system used by the pre-Columbian Maya civilization? They were also used in Central America long back before 876 AD. It's surprising that the numerals consist of only 3 symbols.
Which were they?
0, 1 and 5. 0 was represented as a shell shape, 1 as a dot and 5 as a bar.
What about other numbers then?
You could write up to number 19 with just these 3 symbols.
And what about the numbers that are greater than 19?
After 19, numbers were written in vertical format in powers of 20. Like 433 can be written as 1 into 400 whole plus 1 into 20 whole plus 13. It is represented like this.
Wow, that's good.
Now, why don't we take a quick memory jog and revise everything we have learned today?
Playing with numbers. In this chapter, we study about alpha numerals and puzzles, divisibility tests and puzzles, and finally about the fascinating magic squares. In this capsule, we study about alpha numerals and puzzles. Nearly 2000 years ago, Julius Caesar was busy taking over the world, invading countries to increase the size of the Roman Empire. He needed a way of communicating his battle plans and tactics to everyone on his side without the enemy finding out. So, Caesar would write messages to his generals in code. Instead of writing the letter A, he would write the letter that comes 3 places further on in the alphabet, the letter D. When he go to the end of the alphabet, however, he would have to go right back to the beginning. So instead of an X, he would write A. Similarly, we have problems where letters represent digits which can be decoded. For example, find the values of the letters in the addition of 3a plus 25 is equal to B2. Here, we have to crack the code, that is, find the appropriate digits for the letters. Although cracking the code can be through trial and error method, a little logical thinking helps in getting quick results. Answer. Here is the stepwise procedure based on logical thinking. Step 1. In addition of A and 5, which is giving 2, this is possible only when digit A is 7. In that case, sum of A, that is 7 and 5, will give 12. And 1 will be the carry for the next step. Step 2. After replacing A by 7 and adding 37 to 25, we get 62. Hence, what is B here? B is 6. Therefore, A is 7 and B is 6. Children, here is one more example on addition. Find the value of A in 4A plus 98, which is equal to CB3. Answer. Here is the procedure. Step 1. The addition of A and 8 is giving 3 in the units place. This is possible only when digit A is 5. In that case, sum of A, that is 5 and 8, will give 13 and 1 will be the carry for the next step. Step 2. After replacing A by 5 and by adding 45 to 98, we get 143. Hence, C is 4 and B is 1. Therefore, A is equal to 5, B is equal to 4 and C is equal to 1. Children, Let us now consider the addition of 3-digit coded numbers. Here is an example for you. ABC plus CBA is giving a sum 1242. Here A, B, C are consecutive integers. In the third row, A, B, C appear in some order. Find A, B, C. Answer. Shall we get into the stepwise procedure? Yes, step 1. The sum of digits in the unit place is giving 2. Means C plus A plus another A or B or C is giving 2. And A, B, C are consecutive digits. If another A is considered, it becomes C plus 2A minus 2, which is not possible. Let A is equal to 3, B is equal to 4 and C is equal to 5. Since A, B, C are consecutive digits, if C plus A plus another A is considered, then we get C plus 2A means 5 plus 2 into 3, which is equal to 11. But we have to get 2 in units place. Hence C plus A plus another A is out of question. Similarly, C plus A plus C does not give 2 in units place. Similarly, 5 plus 3 plus 5, which is equal to 13, which is not possible. Step 2. Only C plus A plus B is possible in units place. Here C plus A plus B is equal to 3 plus 4 plus 5, which is equal to 12, and we get 2 in units place. Step 3. Now replace A, B, C by 3, 4, 5. In the two rows ABC plus CBA, we get 345 plus 543. Now, since the unit place of third row is B, it is 4. 5 plus 3 plus 4 is equal to 12 with carry 1. And 1 plus 4 plus 4 plus what is to be placed here is equal to 4 in the sum. Since this what should be 3 or 5. But only 1 plus 4 plus 4 plus 5 is giving 14. Hence, the tens place is C, means 5, and hundreds place must be A, means 3. Now, 345 plus 543 plus 354 is equal to 1242. Hence, A is equal to 3, B is equal to 4, and C is equal to 5. Alternate method. Let A is equal to 3, B is equal to 4, C is equal to 5. Then ABC plus CBA is equal to 345 plus 543, which is equal to 888. Now 1242 minus 888 is equal to 354. Hence, the third row is 354. Therefore, A is equal to 3, B is equal to 4, and C is equal to 5. Let us now consider some multiplication problems involving decoding of letters with numerals. Example, find the value of the letters in AB into 3 giving a product CAB. Here is the stepwise procedure to find a solution. Step 1. The multiplication of 3 and B giving B in one's place of the product CAB. Hence, B must be 0 or 5. Since 0 into 0 is equal to 0, or 3 into 5 is equal to 15. Step 2. Let B be equal to 5. Then AB is A5 into 3, giving a product CA5. with 1 carry. Let us put some value, say 6 for A, then A5 is 65, and 3 into 6 plus carry 1 is giving 19, but we should get 6 for A. Step 3. To get 3 into A plus 1 is equal to CA, this is also not possible for any value of A, and for B is equal to 5. Hence, B cannot be 5. Therefore, the other option for B is 0. Then, A 0 into 3 is giving a product CA0. Step 4. If A is 0, the product is 0. But CA is a 2-digit number, hence A cannot be 0. If A is equal to 5, then A0 becomes 50. And 50 into 3 is equal to 150. Hence, A is equal to 5, B is equal to 0, and C is equal to 1. Children, so far in this capsule, under playing with numbers, we have learned alpha numerals and puzzles.
Hi, this is Presh Talwalkar. Can you place the numbers 1 through 9 in the following 3x3 grid so that each row, column, and diagonal adds up to the same number? This is a condition for the 3x3 magic square. I want you to find all possible arrangements, and I want you to prove there are no other ways to do it. Can you figure it out? Give this puzzle a try, and when you're ready, keep watching the video for the solution. Alright, there are 8 different possibilities for the 3x3 magic square. You'll notice some patterns. Every single square has the number 5 in the center. The corners of each square are made up of the even numbers 2, 4, 6, and 8. The edges are made up of the odd numbers 1, 3, 7, and 9. In fact, every single one of these 8 patterns is really a rotation and a reflection of a single pattern. So what do I mean by that? So let's focus on the magic square in the upper left. I'm going to create a copy of it, and now let's imagine reflecting the numbers through the middle. So this will transpose the first and third columns. This brings another magic square, which was the second square in our list. Let's make a copy of this second square. I'm going to rotate 180 degrees. And now I'm going to bring the numbers right side up. This was the third magic square in our list. Let's make a copy of the first square again. Now I'm going to do a reflection across the diagonal. So this will exchange all the numbers that are across the diagonal with each other. This is another magic square that was in our list. And you could continue. You would actually find that all of these magic squares can be obtained by rotations and reflections, or combinations of rotations and reflections of the first pattern. So they all actually can be obtained from each other. As a technical note, these are actually correspond to the symmetries of a square, or the dihedral group of order 8. So we're going to prove these are the only ways you can have a 3x3 magic square. And we're going to do that in several steps. So first, we're going to say, we don't actually know a magic square exists, but we're going to come up with some conditions that if a square exists, certain things have to be true. So one thing is that every single row, column, and diagonal is going to need to sum to 15. So why is that? Let's take a look at summing up the first row. We don't know what it is, but we'll say the sum has to be some constant m. The second row has to have exactly the same sum because in a magic row, every single row has the same sum. The third row also has to have the same sum. So now let's add up these 3 rows. We have m 3 times, which brings us to 3m. But there is another way that we could sum up the 3 rows. We know that the 3 rows contain the numbers 1 through 9 used exactly once. So we know that all of the 9 rows, all of the 9 elements have to be the sum of the numbers 1 through 9. So we have the sum of the numbers of 1 through 9 equal to 3m, which means 45 equals 3m, and so m equals 15. So if a magic square exists, it needs to have a magic sum of 15. I did this proof using the 3 rows. You could similarly do that proof using the 3 columns. Now step 2. We know that these 3 numbers are going to need to add up to 15. So now we can try and compute the different ways we can get to a sum of 15 from 3 distinct numbers. Let's say we have 1 as our first number, and then we want to add 2. In order to get to 15, we would need to add 12. But that's clearly a problem because our numbers only go up to 9. So we cannot have 12, and therefore we can't have 1 and 2. At most, we could have 1 being paired with 9, which means the middle number would have to be 5. If we paired 1 with 8, then the middle number would be 6. So we can go through these possibilities and figure out there are only 8 distinct ways that we can get these numbers to add up to 15. I'm going to put those sums to the side, but this is the crucial step in the proof. We're actually going to be able to deduce a lot from it. For example, this will be able to tell us the center square has to be 5. The center square is involved in the middle row sum, it's involved in the middle column sum, and it's also involved in the sum of each of the 2 diagonals. So the center square is involved in 4 different sums of numbers. So what possibly could the center square be? If we look at our sums, only the number 5 is involved in 4 different combinations. All of the other ones are involved in either 2 or 3 of the combinations. So that means the center square would have to be 5. Continuing the reasoning, we can find the corners have to be even numbers. A corner would be involved in one of the row sums, one of the column sums, and also one of the diagonal sums. So each corner is involved in exactly 3 of the sums, and this corresponds to the numbers 2, the numbers 4, the number 6, and the number 8. So we know the corners would have to be 2, 4, 6, and 8. And finally, every edge is involved in a row sum and a column sum. So it's involved in exactly 2 distinct sums. If we look at our list of sums that get up to 15, this would be the numbers 1, 3, 7, and 9. So let's put all this knowledge to use. We know that the number 5 has to be in the center. We can put the number 1 right above it. We can put it to the left of the 5. We can put it below the 5. And we can put it to the right of 5. Opposite the 1, we would have to have 9 in order to get to 15. Now, in the perpendicular row or a column, we can put the number 3 in 2 different spots. If you focus on the square in the upper left, we can put the 3 to the left of the 1, or we could put it to the right of the 1. We could put, if you look at the lower left square, we could put the 3 above the 1, or we could put it below the 1. So in each one of these possibilities, we can put 3 in 2 different spots that are perpendicular to wherever the row or the column that the 1 is. And now we're going to have to fill in the 9s and the 7s from the 1s and the 3s that we've put in, because 7 has to be opposite 3 and 9 has to be opposite 1. So these are a total of 8 different possibilities to put the odd numbers on the edges. And in fact, that's the only way that we can arrange this. The odd numbers were involved in exactly 2 sums, so that means the remaining sums are the even numbers. And they're forced by the arrangements we've already made. So these are the 8 different magic squares. They actually do work. These all add up to 15 in each row, column, and diagonal. And so we've proven that 8 of them exist. And by the conditions we set up, these are the only squares that could be a 3x3 magic square. As we've shown earlier, these are all unique up to rotations and reflections. So the 3x3 magic square is really cool. It's only one pattern, and the rest of the patterns are related by being reflections and rotations of the square.
Thank you for watching our channel. இந்த வீடியோ உங்களுக்கு பிடிச்சிருந்ததுன்னா கமெண்ட் பண்ணுங்க, லைக் பண்ணுங்க, ஷேர் பண்ணுங்க. மறக்காம இந்த சேனலை சப்ஸ்கிரைப் பண்ணிட்டு பக்கத்துல இருக்கக்கூடிய பெல் பட்டனை